Fred, ladies and gentlemen, we have 13 at the minute. Let's just maybe wait 1 or 2 more minutes to see if anyone else is going to join us. But as a preamble for today's conversation, how to take the guesswork out of expert judgment. I'm guessing everyone would like to be able to walk away from here being able to do all the numbers and all the math and all the stats. And while there is scope for some of us to be able to do that, the reality is today's discussion is an introduction. The most important thing about today is to let you know what the scope or the art of the possible is when it comes to trying to characterize expert judgment. And engineers and technicians and decision makers and, let's just say, important people can sometimes be quite snobbish when it comes to information. And what I mean by that is we sometimes don't like making decisions based on what some of us derisively refer to as best guesses or subjective opinions. Sometimes we say, I will only make decisions that's informed by information derived from data. And in some cases, that's the right call to make. You sometimes need to make decisions based on information you glean from data. There are certain cases where that is what you need to do. But for the vast majority of decisions, we actually use this wonderful thing called expert judgment. When we design something from scratch, we don't test or gather data to work out if we're going to use a hydraulic pump or a pneumatic pump, or choose between an electrical power source or an electrical motor versus an internal combustion engine. We use this thing called expert judgment. And if you can imagine all the decisions you make personally on a daily basis, I know that you aren't conducting exhaustive data gathering tests for each and every single one of those decisions that you make. It is based on your combined experiences and combined knowledge, what you've learned over the years, this wonderful thing we call expert judgment. And one of the most magnificent aspects of expert judgment is that it is essentially free. Of course, it's not free in that you had to spend time and money going to university and reading books and practicing how to do things. But as of today, if I want to access the expert judgment you retain in your brain, it is now a free exchange of information. It already exists. It's right there. And for that reason, we want to maximize the extent to which we can use expert judgment on a daily basis. Now, before I go on and look at a really cool example, I want to talk about confidence. Confidence is something we talk about a lot in, again, everyday life, but in particular, when we're dealing with reliability and availability and maintainability, we use the term confidence often with a very statistical overtone. That is, we might be interested in understanding some sort of number or some sort of metric or some sort of parameter. And we might want to have confidence that that's our, for lack of a better term, our guess of what that number is within certain limits. So for example, if we're interested in the on-demand reliability of a missile, the mission reliability of some sort of missile, for example, we might expect that our data scientists out there will do some examinations, some testing, some modeling, some analysis, all those wonderful things, and say, you know what? We believe that the reliability, the mission reliability of the missile is 0.99 or 99%. That's our point estimate. But we're 90% confident that it's between 0.985 and 0.995. So that sort of expresses what we call confidence in our estimate regarding some uncertain figure. Now, the reality is there's no uncertainty from the perspective of that missile. The mission reliability, the on-demand reliability is what it is. It is not changing. It's just there waiting for us to learn more information about it. So confidence is a measure of us. It's not a measure of the missile system, the product, the system, the equipment. It is a measure of us. And why that's important is because we can do all sorts of different things to improve or diminish our confidence we have in a certain belief. Now, there are two sorts of confidence. One form of confidence comes from understanding your process. So there are plenty of organizations out there who manufacture really reliable things, and they are very confident in what they do because they understand how to design and manufacture reliable things. And a lot of these organizations don't do a lot of quantitative testing. They know that because they did a FMEA, a fault tree analysis, HALT, or whatever the right design for reliability strategy was for that device, and they have the skills, and you have a leadership team which is invested in creating a culture where you do it right the first time. They don't need to do exhaustive testing to get confidence that what they are doing is going to result in something reliable. So that's confidence from understanding. The second form of confidence is confidence through statistics. Now, statistics are wonderful, it's subjective to an extent, but it can be expensive. I've seen test regimes which last over a year in order to generate confidence in terms of statistics. Now, as a rule, people who demand confidence from statistics are people who do not get confidence from understanding. You might think of classic cases where you have some non-engineer or non-technician or someone who's not familiar with whatever product we're developing. All of a sudden, they're in charge of our program or project or quality assurance. They are not really aware or not have good understanding of what it takes to make something reliable. And these are the sort of people who, for whatever reason, demand that we only get confidence through statistics. Now, of course, there are scenarios where you need to have confidence from statistics. There's also a lot of other scenarios where we can derive confidence through understanding. And understanding is essentially a subset of expert judgment. So what I'm going to talk about now is, after that sort of rambling introduction, I'm going to go through, and I dare say a couple of you might have seen this before if you've done some of my classes or undertaken some of my courses. An example where I wanted to suck the expert judgment out of a bunch of my students. And that sounds quite violent and intrusive, but hopefully by the time you've gone through this discussion today, you'll see that there are ways we can suck this information out. So the scenario I'm going to paint is a class where I'm teaching all sorts of wonderful reliability engineering stuff. And I ask my students regarding a monitor at the front of the classroom, I say, look, we, for whatever reason, are really interested in understanding the diagonal of this monitor, how long that is. Now, the reason why I use this as an example is because this is analogous to any troubling metric we're trying to get a better understanding of. It could be the mean time between failure. It could be reliability. It could be repair rate. It could be estimated time until we think 5% of our products are going to fail, which is a really useful metric for determining warranty period, for example. The point is that we have some metric that, whether we like to admit it or not, there are a bunch of opinions that are stored in people's brain. And this is a good example where we have, in this case, a bunch of my students looking at a computer monitor at the front of the screen. And of course, they will have some sort of opinion about how wide or long that diagonal is. And let's just say that for whatever reason, we're not allowed to measure it, or we can't measure it, or the tape measure's been left at home, or for whatever reason, we cannot physically actually measure this diagonal. And so the challenge is to try and estimate what this length is using expert judgment. And you can use this approach for any sort of number or metric that you come across. Now, what we can now do is treat each one of our students as if they are essentially their own little test, their own little experiment. And this experiment involves these students observing something and formulating an idea of what that means in their brain. So in this case, we have one student who's looking at the TV or the monitor, and she, in this case, is using her combined experiences. Perhaps she's done some carpentry where obviously you need to do a lot of measuring. Perhaps she's worked in an electronic TV store where she's very familiar with typical computer monitor sizes and dimensions. Perhaps she's worked as a seamstress where of course, you need to do lots of measuring. Or perhaps she's had no experience, but has had at least some awareness of basic units of measurement. And what's happening when we look at something like this, we form models in our brain. We compare those models we create in our brain with our existing ideas or concepts about how long a centimeter is or how long an inch is. And we're able to come up with some usually hidden idea about the length of something like the diagonal of this TV screen or computer monitor. So that exists in brains. If every time I ask you to have a guess about something in particular, your brain is going through this process, even if it's not something that's very apparent. Your brain is an amazing organ, can do all sorts of wonderful things. And that's derived from our history as hunter-gatherers, where you have to estimate how far away, for example, our prey is before we throw that spear, etc., etc., etc. So this ability to judge distance and length is built into our brain. So let's just go back to the problem we're trying to solve. We want to understand how long the diagonal of the TV screen is. Now, for the in the guidebook, which Fred has shared the link to in the chat window, which follows everything we're going to go through today, plus a little bit more in terms of a couple of equations if you do want to try and do a couple of these things in your own time. I use inches and centimeters to express lengths, but for those some of our North American brethren today, unfortunately for you, this one is all about centimeters, paying homage to my Antipodean ancestry. So nonetheless, you don't have to get wrapped up in the units of measurement. All we need to understand is that this ruler here, this scale here, represents some sort of way we attribute a quantity to a number. We use exactly the same thing for mass, whether we use pounds or kilograms. Torque, whether it's foot-pounds or newton meters. We have come up with some units of measurement we use to be able to create a language where we can converse and express quantities of virtually anything. So let's just say this scale here is how we measure something. Mean time between failure, years between failure, or months between failure, or operational hours between failure. All those have arbitrary meanings, which we have predefined and essentially set up this scale for us to use. Now, when it comes to sucking the information out of someone's brain, their brain is furiously working away at trying to use this scale, which they have built into their brain over the years, to align this scale with what their eyes or what their hands tell them. And so each student is going to be looking at this particular scale and come up with usually a point estimate. And so in this case, let's just say one of our students looked at the TV monitor or the computer monitor, and in their brain, the brain's best guess at what that length was or is 70 centimeters. But again, that is sometimes not easy to articulate, even though our brain is doing a really good job at judging distances. because centimeters and inches and foot pounds and newtons and everything else, they're human constructs. They're not hardwired into our DNA. We sometimes struggle to easily put a number against this best guess. We often round it to the nearest 10, for example. We might say that's 60 centimeters or 70 centimeters or 80 centimeters, when in fact, our brain's best guess might be 74.39 centimeters in terms of the units it uses. But nonetheless, let's just say we're able to peer into our brain and get a best guess like this. In this case, one student believes that the diagonal of the TV is 70 centimeters. Now, of course, we can't do that. So what do? We ask people, what do you think your best guess is? And of course, one of our students in this case might say, well, my best guess is 70 centimeters. Now, that's all well and good, but this is simply a point estimate, which means I need to bring it back to this conversation about confidence. Say one of our students is an avid hunter, for example, and has to judge distances on a daily basis, or perhaps one of our students is a carpenter and spends every spare minute of every day measuring wood before they cut it. So they see rulers and tape measures like this so often that their brain is really well trained at judging short lengths like this. Or perhaps someone is a seamstress who, again, does lots of measuring. So they are constantly training their brain or reminding their brain what 70 centimeters looks like. And of course, there are students who do none of this, who might do precious little measuring of distances or might be short-sighted, or might have some impediment to generate the same level of confidence as our other students who are actually pretty good or have spent a long time training their brain to be familiar with basic distances like this. So we need to not only just pull out point estimates, because the point estimate from someone who's very confident is way more important than the point estimate of someone who's not very confident about their best guess. And so one way of trying to quantify this confidence is to, while we ask each student to focus on their best guess, their point estimate, and then quantify a tolerance or a range or an error margin associated with their best guess. And so in this case, the student who I asked, what is your best guess, also accompanied or provided with their best guess an error margin of plus or minus 10 centimeters. And in this case, I asked for a third number from these students, from this student, I should say. And I said, well, okay, so your best guess is 70 centimeters. Your error margin is plus or minus 10 centimeters, so 60 to 80 centimeters. How confident are you that the true length is within this error range from 60 to 80 centimeters? And their answer is, in this case, 90%. So let's look at what we've done. We have started to create a language which allows experts, in this case, my students who are judging the length of the diagonal of a monitor or a TV screen, to try and summarize their knowledge, their information, their judgment as it relates to the diagonal of a TV screen. And what this allows me to do right now is to fit this thing we call a bell curve to then characterize the information that we believe is contained in the brain of my student in question. So before I go on, let's take a quick minute to pause and ask if there's any questions, if there's any anecdotes, any stories, any comments before we move on with trying to use this expert judgment to help us make better decisions. Any questions? Questions, comments, opinions, thought pieces, essays? Okay, so before I move on, could I just ask through a show of emoji-based hands, Who has heard of the bell curve / normal distribution before? Excuse me. See a couple of hands going up. So quite a few of us have heard of it. I dare say some of you are struggling to find where to raise your hand in this digital platform. And so I'm going to assume that perhaps a good chunk of us have heard of this thing called the bell curve or the normal distribution. Fantastic. Now, the bell curve or normal distribution is seen a lot in the natural and physical world around us. And the reason why is because the bell curve actually models random processes that are the sum of lots of other random processes. For people who have endured my conversations in the past and may have come across this normal distribution bell curve conversation, this might be a bit of revision, but it's really important because a lot of the processes around us are based on adding things together. So for example, when we measure the height of human beings, which is a random variable, we often see a bell curve. And the reason why is because human height is actually the sum of lots of random processes, which includes DNA, genetics, diet, exercise, injuries, health conditions, diseases. All these things in our history combine in an additive way to influence how tall we are. Even identical twins are not exactly the same height. And that can only be caused by natural variation in the world around us because our height is based on the sum or the aggregate effect of lots of random processes. So we see this bell curve in the natural world around us. In fact, the bell curve was actually created before we realized this really cool feature of it. It was used to model astronomical errors. When I mean astronomical errors, not errors made by astronomy. Astronomy is a field of study or research. No, the measurements that astronomers were making regarding celestial bodies, there were inherent errors in those measurements, those things we were trying to estimate through images we saw on telescopes. And it was found that this bell curve was really, really good at modeling those errors. And it turns out that that's because when we make a measurement error, that's the sum of lots of random processes, where our eyeball is, where the datum is, errors in random processes regarding the actual direction of telescopes versus what it says on gauges, so on and so forth. There's lots of random processes which add up or combine to create errors in our measurements. And it just so happened that the bell curve was coincidentally found to do a really good job of measuring those errors. And a couple of 100 years later, it was we worked out why. And so the bell curve is often a really good way of modeling uncertainty in the human brain, because the human brain uses lots of processes to, for example, estimate the length of the diagonal on a computer monitor, which is fantastic because we now know that the bell curve is going to be really good at modeling the uncertainty we have in people's brains. Now, this means that one person's brain, in a way, is represented by this bell curve you can see on the screen, which means that we now have some sort of quantitative shape to characterize everyone's uncertainty. So this is the actual set of bell curves I derived from my students in this course. And you can see that some were way more confident on the diagonal length, the diagonal of a TV or computer screen than others. So there were people who are way more confident, who believed they had a much smaller error margin. They had the really tall, narrow bell curves. So those ones who weren't really confident at all, those bell curves were very short and fat because there's lots of uncertainty. And then we use this thing called, wait for it, Bayesian analysis. That allows us to take all these sources of information and combine them in a way to create what we call a posterior distribution. And so in this case, the posterior distribution, which summarizes all this different information that we got from each one of my students, looks like this. Now, this clearly this red curve here, which looks like a bell curve, and it's very, very close to a bell curve. We can show that if we had lots of information sources, it looks closer and closer and closer to a bell curve. But the really important thing here is that this posterior distribution is a lot more certain, or has a lot less uncertainty than any of the students' expert judgment. And so when we combine all these expert judgments, all these information sources, all these sources of knowledge, we get this wonderful posterior distribution, which is very concentrated around a certain region. And that allows us to have a lot more accuracy in things we're estimating. And so this posterior distribution allows us to generate what we call a state of knowledge or sense of information that involves a lot less uncertainty than if we were trying to individually estimate the length of the diagonal on the TV screen. But of course, most of you are going to be really interested to see how long the actual diagonal of the TV screen was compared to this posterior distribution. Well, you can see the posterior distribution, this red curve, it seems to range from between 72 to 80 centimeters. Well, it turns out the actual diagonal length of the TV was 76 centimeters, almost right in the middle of this posterior distribution. Now, I have done this experiment over and over and over and over again. It's very powerful because every time I do a course when I have actual students in a real classroom, which hasn't happened as often as I would have liked as recently because of COVID. But every time I get to teach this lesson, and every time I have live students in a course and I have enough of them, I run this experiment, and we use either the length of a window or length of a TV. And then after we go through this process, we quickly work out the posterior distribution. Then I bring out a tape measure and work out how long the actual thing we're all estimating is. And it turns out that without fail, the results typically look like this. We usually get a posterior distribution, which is very, very, very close to the actual metric we're trying to understand. And this should give you an insight into the power of expert judgment. So just imagine if you had 10, 15, 20 people who are going through this process of estimating warranty reliability for a product that they're developing. If you could get results like this in 20 minutes, which would possibly be way more accurate than your than years of testing, why wouldn't you do this? Well, one of the reasons is because of cultural hangups with subjective estimates, as we sometimes call it. But the reality is, if you are comfortable with the state of knowledge of your team, then you can get some really powerful results very, very quickly. And this is the world of Bayesian analysis, which gets a bad rap because, again, a lot of statisticians out there believe that this simply is all about subjective estimates. And so it's opinion-based, not fact-based. And that's an unfair slur against what Bayesian analysis is. But if we go back to the scenario we're just looking at, each one of these gray bell curves represents a single expert opinion, a single source of expert judgment. But in practice, this could be any information source. It could be information information as it related to a previous model of the product you're looking at. It could be from a textbook. It could be from any source of information you have, which is what makes Bayesian analysis very, very powerful, because it can still use test data. You can use expert opinions, any information source, and test data to try and create a posterior distribution which combines all that information. So Bayesian analysis can do all this stuff. Now, just to get a bit of statistical terms out there, these gray curves here are what we call likelihood functions. Likelihood functions are essentially the likelihood that our metric in question, an unknown of interest, assumes a certain value given a certain form of evidence. And in this case, the evidence I received was those three numbers I received from each student: their best guess, their error margin, and their confidence. And for each one of these sets of evidence, I was able to create essentially a likelihood function based on the model, which was the bell curve, which looked like this. And in the guidebook, you have the math that helps you work out how to create a bell curve based on the best guess, where you ask someone about their best guess, error margin, and confidence. Now, in this case, when it comes to Bayesian analysis, you need to have what's called a prior distribution as well. The idea is that we are updating our knowledge, our information, whenever we gather new evidence. So we have to start somewhere. And as a rule, we try and use what's called non-informative priors which represent a complete lack of knowledge. Sometimes we make a prior distribution completely flat to say it's equally likely to be 10, 20, 30, 40, 50, 60, all the way up to 100 centimeters. But there are some reasons why this is not perfect. But if you have enough sources of evidence, the prior distribution becomes less and less important. So for 20 students, in this case, the prior distribution is less important. And the idea is that the prior distribution represents my understanding before I gathered the evidence, but I got the opinions of 20 students and was able to turn that flat prior distribution, our prior understanding or state of knowledge, into an updated understanding or a posterior state of knowledge when my computer decides to update the state of knowledge on the shared screen, which it's not doing right now. There we go. Oh, we went too far. And the idea is that Bayesian analysis allows you to update your state of knowledge, which is represented by these curves, these lines, as we go. And this all starts with the concept of the likelihood. The likelihood is something we see in statistics wherever we go. Doesn't matter whether you're doing Bayesian analysis or what we call classical or frequentist analysis. We use the term likelihood because it's the staple of statistical inference. So I know a lot of my people who follow my webinars and courses are very familiar with the good old random hand of failure, which is simply a chart, an illustration to characterize or summarize all the different sources of variation or uncertainty in a process such as failure, because failure is a random process. And the reality is, even though we can look at machines and say, hey, those two machines are essentially identical from our perspective, they are manufactured on the same day by the same crew on the same production line, even seemingly identical machines will have some underlying variations, which means that they will fail at different points in time. And those variations are usually nothing compared to the variation in how customers or users will ultimately use those seemingly two identical machines, which means that no matter what happens, we will have different times to failure for seemingly identical things because it's a random process. So in this case, the gray curve here is what we call a probability density function, and that sort of characterizes the inherent uncertainty in this case, this particular random hand of failure. And you can see that the data points, which represent individual times to failure of different machines or pieces of equipment, seem to congregate or have a higher density around the regions where the PDF curve is highest. That's all that the PDF curve does. It just summarizes the density within which we expect random variables to assume certain values. Now, you can see that perhaps in this case, there's a clear correlation between this PDF curve and this data we observe. It seems like that the data is indeed densest where the PDF curve is the highest. So let's just say that this curve we designate as a likely candidate PDF curve to describe whatever it is we're seeing. It seems that it seems to align with the data that we observe. But of course, there's lots of other candidate PDF curves out there, such as this one, which is what we call an exponential distribution. Now you can see that this PDF curve doesn't really look like a smooth curve we saw in the previous animation where it looked like a bell. This PDF curve looks like a ramp where the most likely random variable value is actually at or close to 0. Now we can see that this PDF curve clearly doesn't describe the density of our observed times to failure of data points. It clearly doesn't. So we might be able to say that this PDF curve is less likely to represent the random process generated these data points. And essentially, if you understand that, you understand what likelihood means. Likelihood is all about whether the data supports some underlying idea of what's going on. People who maybe originally thought this PDF curve might describe the random process we're observing, well, as soon as we see the data points, you should be saying, well, you know what, my first guess at what the underlying random process was is becoming less and less likely. It's not impossible, but it is less and less likely because the height of the PDF curve does not correlate with regions of highest density for our data points. And so that's what likelihood is. But of course, when it comes to statistics, we need to do a little bit more formalization. So this PDF curve is, hopefully you can understand what it represents in terms of the density or frequency, or where we expect most of these data points to occur. It is based on this probability density function, which tells us the relative probability that a continuous random variable is equal to a specific value. And we often denote this particular curve with the notation lowercase f followed by x in brackets. It simply tells us, or we use this to define different types of different ways random processes are going to generate outputs. So in this case, the PDF curve, this gray PDF curve, looks like it does indeed align with this data because it's the highest part of the PDF curve aligns with the most dense region of our data points. So let's just say this could be, if we knew nothing else, if someone said, hey, I think it could be this gray PDF curve, what do you think? You say, well, you know what? It seems to be a relatively good fit. But we need to turn that into a number because when it comes to statistics, we do need to eventually convert ideas and opinions into numbers. And the way we convert the likelihood of this particular PDF curve into a number is simply drawing a line up from every single data point to where that line intersects at the top of our PDF curve, because each one of these lengths of these lines here gives us the relative probability of each one of these data points having that value according to this PDF curve. And essentially we multiply all these heights together to come up with a number which then characterizes the overarching likelihood of this PDF curve describing our random process. Of course, if we were to do the same for our exponential PDF curve, the exponential distribution, you can see that the line's going up on average a lot shorter. When we multiply these heights of each line together, the likelihood goes way down. So we start coming up with numbers that allow us to essentially quantify the likelihood of things like different PDF curves and different models. And that's essentially, if you understand that, you understand what likelihood is. So what makes Bayesian analysis very different from everything else that we tend to be taught first in textbooks and classes and lessons and things like that? Well, most of the professors and doyens of statistics we first get introduced to are essentially this guy here, when he eventually comes up, the classical statistician, what we call the frequentist. And this professor, this statistician might say something like, it is with 90% confidence that I say that mission reliability is greater than 0.99. And what that actually means is very different to what we usually take away from a message like this. So what that means, we might look at this sort of statement here and go, great, there is a 90% chance that reliability is greater than 0.99. Now we go back to our professor, back to our classical statistician, and he would say, I didn't say that. And then we would then, in response to this response to our response, go, what? Didn't you just say that it is with 90% confidence I say that mission reliability is greater than 0.99? And now we're very confused because we take this sort of statement and conclude naturally that this person is telling us there's a 90% chance that the mission reliability is greater than 0.99. But he says, no, that's not what I'm saying at all. So what does that mean? So what is a probability that mission reliability is greater than 0.99? Because it's something we need to know in order to make a decision about whether we are there yet. Anyway, our classical statistician, he will theoretically at least say, I can't work that out for you. I don't work that out. That's not something I do. And now we are beyond confused. The reason we're beyond confused is because classical statisticians, frequentist statisticians, essentially, when they say things like confidence, what they actually mean is that for every 10 times I say something with 90% confidence, you would expect me to be wrong once. And so this person isn't actually saying whether what the uncertainty is on our particular metric. They're essentially expressing the uncertainty on them being right. Now, this might seem like semantics, but the reality is that when we see phrases like the phrase that our statisticians first told us, we go away and make decisions, presuming that he is telling us that there's a 90% chance that mission reliability exceeds 0.99. But in practice, classical statistics, frequentist statistics, doesn't ever come up with what we call confidence bounds. They actually talk, it's all technically, from a theoretical perspective, it's all about the probability of them being right or wrong. And of course, this doesn't help us at all. So we need to either do a couple of things. We need to look at this person, understand what frequentist probability is all about, classical school, the non-Bayesian school. And the frequentist probability is sometimes misused in business cases and things like that, because we take statements based on frequentist statistics, classical statistics, and we interpret those basic statements as, for example, saying that there's a 90% chance that reliability exceeds 0.99. This is a sort of phrase we need to be able to digest and put into a business case when we make a decision. And the reason why there's this confusing, horrible semantic argument between what I'm saying or what I'm suggesting you need to interpret from the classical statistician and what seems to make sense in our mind is because Bayesian analysis is all about subjective probability, and Bayesian analysis is one way of essentially mimicking how the human brain thinks. Our brains are essentially Bayesian. Our knowledge is based on what we have experienced up until today. Our knowledge at the end of today will be different because we have observed things, we have updated our understanding of certain things. And so our brain is inherently subjective, which means that our brain is inherently wired to be Bayesian. It is not wired to be classical or frequentist, even though that is what is taught in a lot of textbooks. And so this subjective probability is something which comes very naturally to us, even if we don't understand it, at least in terms of a definition. Human beings in Bayesian analysis are all about subjective probability. You might think that the stock market has a certain percentage or a certain chance of increasing, but then you read some reports or you see some some reviews in the Financial Times, or some news comes around about what's happening in the global market, and then you're going to update your beliefs about where that stock market is going to go. You might have a belief regarding, for example, a mining company, which is all about rare metals, I should say, like lithium, which is used in rechargeable batteries. Now, your estimation of how that company is going to perform will possibly improve or increase if you also learn that there has been a huge contract signed for an electronic vehicle manufacturer to provide vehicles to, I don't know, a military force or a large customer, because that then implies it's going to be increased demand on rechargeable batteries. So therefore, your belief regarding how that mining company is going to perform will probably modify. You'll probably amend your beliefs to align with an improved or exceeded higher expectation of how that company is going to perform. But in practice, most textbooks are all about frequentist probability. Every textbook, though, says essentially once you get frequentist conclusions, just act as if it's subjective, and then you make decisions based on that assumption. Now, the reason why this is bad is outside the scope of this webinar, but I'm trying to at least articulate there are some things that you need to perhaps dive more deeply into when it comes to statistics. And sometimes that dive can confuse you further, but if you do want to investigate statistics in a more detailed way, it can more often than not, if you take it seriously, help provide clarity for what could have been previously confusing scenarios. So let's go back to Bayesian analysis and how I was able to take the expert judgment of 20 different students and come up with a really wonderfully accurate estimate of something that for whatever reason I couldn't measure. In this case, the diagonal of a TV. Now, frequentist statistics can't do this. Frequentist classical statistics can only is only based on this thing called the uniform prior distribution only, and it can only take into consideration experimental data. That's one of the shortcomings with frequentist statistics. And so that means that you cannot take into consideration expert judgment when you use classical statistics. Bayesian statistics is not nearly as discriminatory. It can use any information source. It can use any sort of prior distribution. It can use information or data from a similar system. It can use imperfect data where you know there's some errors in where those numbers come from. You just need to model what those errors are. Expert judgment. Any form of information can be fed into Bayesian statistics, and you can use any prior distribution. So for example, let's just say someone had conducted Bayesian analysis 3 weeks ago on a particular metric, and they created a posterior distribution. Well, you can now use that posterior distribution as your prior distribution and combine that with any additional evidence that or information you've since come across. And that way we keep updating what we call our state of knowledge. Frequentist or classical statistics cannot do this. And that is, and the only way you can sometimes pretend you do this is if you treat frequentist probability as if it's subjective. And as a rule, no one knows when we do that. Most of the time people do it inadvertently and they don't understand why. So if you do this, and you probably do, then you're doing a weird case of Bayesian analysis. But the reality is Bayesian analysis is a wonderful way of taking into consideration expert judgment by turning best guesses or opinions into numbers. So let's look at how this can help us for another scenario. So let's just say that we have a manufacturer of engines or a producer or a reseller of engines. And one test showed that 1 out of every 20 engines was defective. So that's 5%. Now, let's also say that we sent out a quick 1-question electronic survey to 1,000 customers, and we got 48 negative responses. Now, we know that not everyone's going to respond to a survey. Sometimes people who have negative experiences are more likely to respond to surveys because they want to be heard. But people who don't have any negative experiences, they expect their experiences to be positive. They're perhaps less likely to respond to surveys like this. So let's just say we walk down to our marketing team, and the marketing team says, well, in our experience, if someone has a negative experience, they are 60% likely to respond to a survey like the one we just sent out. However, if someone has no negative experience, they have a positive experience, there's only 1% chance of them responding to a survey like this, where they say we had a good experience. It's just nature of the beast. People who have negative experiences are typically louder. They tend to say more things. They tend to want to be heard. And so even if you have a survey where you have, let's just say, a large number of negative responses, it doesn't mean that represents the actual fraction of products or actual fraction of customers who have a negative experience. But we can take this information, combine it with Bayesian analysis, or use it in Bayesian analysis to come up with a really useful summary of what is going on. In this case, we want to understand what the true or what the actual percentage of defective products is. And we have a test, we have some opinions, we have a survey, and when we combine all this stuff together, you can get something which looks a little bit like this. A curve, which is not quite a bell curve, but looks like a bell curve, which summarizes our knowledge based on the test data, the surveys, and our marketing team's understanding of customer reactions to those surveys. So this is based, again, on that original test data, expert judgment, and survey responses. Now, that might mean that you have now saved yourself years or millions of dollars worth of testing to get an understanding like this. And the other thing is that we need to understand that when it comes to testing, we often think testing is the gold standard. It is as perfect or as objective as it can be. But in practice, when we test products, especially when it comes to reliability, the environment we create for those products to be tested sometimes doesn't really mimic or represent how customers actually use our product. So even tests where we spend a lot of time trying to make them perfect and representative are often not very useful, because our customers find really weird and inventive ways of using our products to suit their purposes, which is not abuse, by the way. It's just the nature of the marketplace. So what does that mean? It might mean that actually using surveys and marketing team judgment is going to give you a lot more useful information that goes beyond any hypothetical test you could possibly conduct, because it is the customers who are going to ultimately be the arbiters of whether your product is good, bad, or indifferent. And they don't necessarily sign up to the beautiful test mission profile you come up with for your particular product to help you generate what you think confidence is when it comes to this sort of decision making. So, by the one last thing when it comes to Bayesian analysis, which is seen as a black art, which is seen as some sort of magical thing, which is seen by something which is used by, let's just say, hippies or extremists or people who believe everyone's important. Lots of nonsense out there that is ascribed to Bayesian analysis. It's also seen as something that's very, very complicated. It's actually a lot easier than you might think. But to be able to make it happen, to be able to convert all those expert opinions, all those bell curves that I got from my students to help me understand the diagonal of a TV screen, it is a subject of a course in its own right. I used to think I could do it in its own webinar, but I certainly can't, especially when we need to go through step by step to make sure we understand the steps. But once you do understand the steps, you might be surprised about how easy it is once the context of Bayesian analysis is explained to you in greater detail. And it is a very, very useful way of making the most of the information you have, because we are surrounded by information. Our classical statistician, our frequentist statistician, always complains that he or she never has enough data. Bayesian statisticians instead complain we don't use the information we have well enough. So we have 10 minutes before this meeting is scheduled to end. Are there any questions? Any comments? Any anecdotes? Any stories that relate to anything I've been talking about today when it comes to expert judgment and how we use it? Oh, I needed that drink. Okay, so I have a couple of questions for you, which will hopefully help me understand where you guys are coming from as well. If you don't mind typing into the chat window, if you turned up today with a preconceived idea of a metric you wanted to gain better understanding of through expert judgment, if it's, for example, MTBF or mass or velocity of a device or time to failure or warranty period, what sort of metrics are you interested in using expert judgment to better characterize. Interested to see if anybody has time to failure. Occurrence rating for design for me is fantastic. So occurrence ratings are subjective numbers associated with opinions regarding how frequently failure modes and failure mechanisms are going to occur. Customer reviews or sentiment, fantastic. So that's not a million miles removed from the scenario we looked at the end. Customer satisfaction. Weibull distribution on MTBF versus MTTR. Okay. Building confidence with low amount of test data, fantastic. So you can combine test data with expert judgment. Minimum handle force required to prevent inadvertent movement. To design for MIA rankings, fantastic. So one thing I'll mention while people are still typing in their metrics, when I got my expert judgment from my students, I had to train them. And what I mean by that, I had to teach them how to communicate or express their knowledge. And so we went through a couple of practice exercises where I asked them to estimate my height. I said, I want you to give me the best guess, your error margin, and your confidence. And of course, when they estimated my height, that's where all the people who didn't actually understand how to communicate their confidence, they made the mistakes. Some money included 2 numbers, some included percentages instead of a range for their error. And then once we went through that process, people then understood, oh, okay, so now I understand how you need me to communicate my state of knowledge. And so I had to train people on how to communicate their state of knowledge. That's the first thing. Once they were all trained, the second thing I had to do was ensure anonymity. So they, if I was to ask someone to shout out their best guess, that will, without a shadow of a doubt, influence subsequent guesses being shouted out, especially if someone had a best guess which is greatly exceeds everybody else's best guess. They might, through embarrassment or otherwise, adjust what they believe or shout their best guess out to be to try and align with the group. They call that group consensus. It's a very human thing. And the problem with that is we don't want that. We want a natural representation of our experts. We want to have experts who come from all walks in life, some who are pessimists, some who are optimists, some who are experienced in this field, some are experienced in that field. So we need a balance of opinions. And so to make sure that the opinion of one person doesn't influence the opinion of the other, I had to use anonymity. And all I did was ask everyone to write those 3 numbers down on a piece of paper and forward those pieces of paper to me. So not only did those numbers not assign to any one particular person, they were unable to see what other people had written when they formulated their numbers. So for those people who talk about design for MIA rankings, you can follow the same path. Firstly, train your people to come up with these rankings. To be honest, you could go one step earlier and say, focus on having ranking criteria which are articulated to or relevant for your organization. A lot of people use just ranking criteria for occurrence that I've drawn from standards or drawn from how we always do things. If you can use language so that relates to your product, that's fantastic. There's no point talking about failures or parts per million defects in a ranking system for a missile. A missile is all about mission reliability. Parts per million defects are usually aligns with high rate of production or large scale manufacturing. So use terms in your ranking terminology for design for MIAs that make sense to your scenario. Then train your FMIA participants on how to use that. use those as scenarios, and that might mean that you have a little session beforehand where you go through a couple of example scenarios, and then people practice assigning scores to these scenarios in order to become familiar with how these criteria align with their best guesses. And then finally, once you conduct your FMEA, one way you can get some really useful FMEA rankings, and I always try to do this when I facilitate my FMEAs, is ask them to submit their FMEA rankings anonymously. And that can be done again by a piece of paper or even text messages, where I get a bunch of people's ideas on ranking, and I simply average it out. That means that I have a pretty good spread of ideas regarding FMEA rankings, and that means I'm able to get everyone feels like they've had equal input, because they have. But I'm also ensuring that through anonymity and training, that these guys are doing their level best at expressing their expert judgment without being influenced by anybody else. So hopefully that helps those design FMEA people out there as well. Okay, I've been doing a fair bit of talking. Has anybody got any final comments or questions? Show of hands, perhaps, if anyone. Have I used the Dempster-Schaefer theory? Yes, Larry, I have. Well, I have used it, yes and no. I haven't actually used it to come up with certain outcomes, and I know you're referencing the paper we talked about beforehand. It has been part of a, let's call it literature review I've done for problems which involve expert opinion. But no, I haven't used it to come up with a number. I've used it again to fulfill part of a literature review for an expert judgment problem, but there are some shortcomings I would suggest. But I'll keep that outside the scope of this webinar, if that's okay, because I think people might be done with anything beyond Bayesian analysis. Paul asks, your last point on occurrence, would you use mean or median to exclude outliers? For me, I wouldn't. I tend to use the mean, and the reason why I tend to use the mean is because, again, the median is used to exclude outliers. But when it comes to FMEAs and stuff like that, and FMEA teams, no one should be an outlier. And an outlier is someone who is outside of the mean, or not the mean, sorry, outside of what you expect, someone who is not representative. So outliers are, I believe, are a term that's used a lot. But if you have a good cross-reference or cross-section or good representative team in your FMEA, I would expect that different opinions reference different experiences which you want to incorporate, versus allowing you to include the possibility of outliers. So I use a mean for that reason. I don't. Outliers is a term which is used, I believe, too much, and none of my team, if they're selected properly, should be an outlier. They just might have a different experience base which you're actually trying to incorporate into your discussion. Robert asked, how many experts do you need to approach the accuracy you need in your screen measurement? That was 20 in that case. But that is a difficult question to answer, because the accuracy you get is a function of a few things. It is a function of how confident each one of your experts are. So, for example, if each one of your experts are confident, that you would need fewer than 20 to get the same level of accuracy you observe in the experiments I showed you. So that's the first thing. The second thing is, people often ask, and I know you're not asking this, Robert, but I'm going to answer this question anyway. How many experts do I need total? The problem with that is that depending on the question you're trying to answer, you need different accuracy with your conclusions. Sometimes if you're trying to, if you need to demonstrate the reliability exceeds 90%, but your 5 experts all with confidence conclude that reliability exceeds 99%, then you don't need nearly as many experts, because the question or decision is all about a relatively low bar. If that bar is a lot closer to 99, you might need quite a few more experts and maybe combine that with some test data to get the accuracy you need. So hopefully that helps answer your question. But in the scenario we just looked at, that was 20 people. But that is you won't get that repeated in every single scenario, not a problem. Okay, I think I've exhausted everyone and exhausted all the sources of question. Thank you, Fred, for sharing Larry's article, because Larry's article gives you a good insight into some of the very into an application, a very statistical application where expert judgment was incorporated into a decision-making process. And of course, there's plenty of scenarios out there that go beyond simple Bayesian analysis, although some of us don't call it that simple, that allow us to convert best guesses, for lack of a better term, into meaningful information. There's things like fuzzy logic, and there's things like, I'm having a mind blank right now, but as you know, there's plenty of ways you can convert best guesses into a number to help you make a better decision. However, I find that Bayesian analysis has been, without a doubt, the most universally robust and useful approach in my dealings, where I've had to convert best guesses into numbers to make a decision. So, any last call for questions or comments? Okay, ladies and gentlemen, as always, it is a pleasure talking to you guys. If you have any suggestions about what we need to do moving forward at ascendoreliability.com, please feel free to reach out. We do try and tailor webinars to the requests of people like you. If there's any things we can do to improve, if anything we've done well, that's fantastic. Please let us know as well, because we need to know what we should keep doing and keep doing harder. But beyond that, hopefully you enjoy the rest of your day. Thank you, Dave, Robert, and Elise. Frederick, thank you. Keith, likewise.